Everyone. In the last class, I discussed about the charge, its nature, its characteristics, and basic things related to charge. I told that whatever is available on the fundamental particles of a material like electrons and protons causes some effect in the outside world observable. So the reason that causes these effect is charge. This is available opposite in nature on the two fundamental particles, protons and electrons, and another particle, neutron, is having no such kind of availability, or due to neutrons such kind of effects are not observed. So this is electron on proton on which something is possessed, due to which the effects are seen in the outside world, and mainly we find the effects in terms of the mechanical force that it applies, attraction and repulsion forces. In your book there is one more question given in order to evaluate and to quantitatively know about charge. So before I discuss the today's topic, Coulomb's law, let us understand how or what is explained in this question. This question tells how much positive and negative charge is there in a cup of water. It is assumed that the cup of water is having 250 grams of water. So cup contains 250 grams of water. To calculate amount of charge present in it. You know, charge on electron or proton is 1.6 into 10 to the power minus 19 coulomb. This is its magnitude. On proton it is positive, on neutron on proton it is positive, on electron it is negative. Now atomic mass of water is H2O, you know, so that is water H2O equal to 2 plus 16, that is 18. So number of moles present in cup number of moles for water considered equal to 250 upon 18. You know that 1 mole will be weighing according to its atomic mass, molecular mass. Keep it as molecular, it will be better because water is a molecule. Molecular mass of water is this. Now 1 mole is similar to 6.023 into 10 to the power 23 molecules. Now, total number of electrons or protons present in one molecule of water is what? So there are 2 hydrogen atoms, so 2 for hydrogen plus this is oxygen, 1 atom of oxygen for oxygen, so altogether 10. So altogether 1 molecule of water, thus 1 molecule of water is containing 10, write like this, 1 molecule of water contains 10 charged particles of each type. So combining them all together, total charged particles in given water equal to 250 upon 18 into 6.023 into 10 to the power 23 into 10, and that will be equal to, just have the calculation, 250 upon 18 multiplication 6.023, that is giving 83.652 equal to 83.652 into 10 to the power, this is 23 and 110, 10 to the power 24, and that will be equal to 8.365 into 10 to the power 25. So these number of charged particles are available, and it is known that the charge on 1 electron or 1 proton is given, it is known 1.6 into 10 to the power minus 19, so you can calculate the total value of charge available. So just multiply, so total value of charge equal to 8.365 into 10 to the power 25 into 1.6 into 10 to the power minus 19. Actually, these part-wise calculation I have done to make you understand the thing properly. Otherwise, in general practice, we do all the calculations together. So that is equal to multiplication 1.6. So this is coming 13.38. 13.38 into 25 minus 19, it will be 10 to the power 6, and that will be equal to 1.338 into 10 to the power 7 coulomb. So in this way, actually considering this problem is just to understand about the quantization of the charge and the fundamental value of charge that materials have, because every calculation and everything one has to do in terms of these quantized value. So that is the significance of this problem. Now let us come to find the way of evaluating the quantity of charge. You know, practically or fundamentally or significantly, whatever is the observable effect of charge is there, that is the force that it applies, and we have the means of measuring the force. So the scientist Coulomb in the early time considered this particular characteristics of applying force of the charged particles as the key to evaluate the amount of charge, or in fact the value of charge he explained, or he termed or standardized in terms of the force experienced by charged particles. Now it was observed practically by Coulomb that it is a fact that charge apply force. But in what way the nature of this force changes? Then first thing is that the amount of force, the value of force, or the extent of force is directly proportional to the product of the amount of charges. And then second assumption, second observation was that this force is inversely proportional to the distance between them. According to, and this in fact the significance, or this in fact the observation of Coulomb's law. Coulomb's law tells force experienced between two charged particles is directly proportional to the charges, and inversely proportional to the distance of observation point from the test charge, or inversely proportional to the distance between the two charges. Now this is totally a practical observation. See, you have suppose two balls or two objects, and there is some meter or some scale to measure the force applied in them or force experienced by one object by another. Then it was observed that when the value of charge is increased in either of the balls, then there is significant increase in the force observed, either on this or on this or on both. When the charge amount of charge is increased, the objects can be charged by induction or by any mean it is charged. Then as the charge is increased on the two particles, on the two objects, then increase in the force is observed. Second is that when the separation between the two balls is done, then when the balls are made closed, then increase in the force was observed. When the ball was separated, then decrease in the force was. I'm not talking anything about the direction of the force, but in the value of the force, this was practically observed, and then it was written like that. These are the observations. On this basis, it was written like F is proportional to Q1 Q2 upon R square. Here Q1 and Q2 are the value of two charges, and R is the separation between them. Again, I repeat, this is a practical observation. In order to evaluate this, a constant of variation is considered, and then F is considered equal to 1 upon 4 pi epsilon 0 into Q1 Q2 upon R square. Here epsilon 0, epsilon for vacuum, it is marked as epsilon 0 and its value is 8.854 into 10 to the power minus 12. Wait for the unit of this. Now this is a constant quantity. In fact, see, again this is right now I can talk the things on the basis of experience only, experience of the scientists which proposed these laws. Again, it was experienced that the medium in which the observation is done has some effect on this force experienced, and this particular effect or this particular change in force is independent of charge and the distance. Whatever the proportion is changed due to change in medium is applicable on all the experiments of different charges and different distances. So the effect of this material had been taken as the constant quantity in finalizing this variation in order to calculate the force, and by different other means this value was observed as 8.854 into 10 to the power minus 12. So altogether the constant of variation in this case is taken as this. This is constant quantity for a medium. So this finally about this force, when you talk 1 upon 4 pi epsilon 0 into Q1 Q2 upon R square. Now till now I am considering only about the quantity of force, amount of force. What about direction? Because force is a vector quantity. When you talk about a force, there will be a line of action of the force. Without direction, force cannot be applied. These are the things of mechanics, But when you talk about force, there is a direction associated with it. So in the Coulomb's force also, in the electrostatic force also, when the term force is considered, it is necessary to consider in which direction it is applied. So this direction generally is along the direction of the line of the two charges, whether towards the charge or outward the charge. And if you want to consider this on a plane or in the space, you have to consider the vector norms for calculating the exact direction of the force. And for that, in vector notation, in vector form, you have to tell the position of charge Q1, the position of charge Q2, and accordingly the position of the line of action of the two charges can be determined, and then the final direction of the force can be told. For example, let us consider this is the origin, means the reference point with respect to which you are talking about the position of the 2 point charges. This is Q1 and this is Q2. This is position vector R1 and this is position vector R2. I assume that about these position vectors you are knowing, or see, if you are talking about a plane, then in a plane an object has a coordinate, a point has a coordinate. That coordinate can be explained either in terms of x and y, or actually I am explicitly telling this thing because quantitative calculation one can do easily in the first phase, but in vector considerations people feel difficulty because they hardly imagine or hardly visualize in what way these vectors are practically observable or practically experienced. So in a plane, when some point is there, then in coordinate geometry you have studied that any point of the plane is explained, is told, is expressed. So let us consider on a plane itself the two charged particles are not. I am not considering on the space. Actually this is the case of the space, and same is in the space also. If x, y and z coordinates are there, and suppose you have to tell the position of my head, then that you can tell from that corner my head is shifted this much distance in x direction, this much distance in y direction, and this much distance in z direction, and from that point whatever the resultant will come from that point to my head will be the position vector of my head with respect to that corner. So similarly, the position of the two charges are there to be expressed by position vectors R1 and R2, and the resultant will be either in this direction or in this direction depending on the situation. So, but it will be in either of the opposite direction, the direction of force is taken. But one thing is clear, that the resultant of the position vectors R1 and R2 are along the line on which the charges Q1 and Q2 are existing. We are considering the point charges. So one line can pass through the 2 points. So along the line only there will be the line of action of the forces will be there. It is another thing depending on the nature of charges, that charge will be towards Q2 from Q1 or towards Q2. The charge will be from Q1 to Q2 or from Q2 to Q1. But one thing is fact, that it will be in the on the line of joining two charges Q1 and Q2. So let us consider a unit vector R along the line if the direction of this force is along the line joining the two point charges. Considering a unit vector along this line R the equation can be rewritten as F equal to 1 upon 4 pi epsilon 0 into Q1 Q2 upon R square and R. This is the overall expression. Value of epsilon 0 is calculated by some other mean as 8.854 into 10 to the power minus 12. Now to consider its unit, again leave the unit. Because in terms of one, another is explained. So since here Q1 and Q2 I am keeping for granted that we are not knowing about it. So I'm not considering this unit right now. So consider Q1 equal to Q2 equal to, assume 1 see, keep focused on the word this assume. I am not knowing what is 1. Amount of charge assumed as 1 and R is also considered 1 meter apart. Then F will be 1.4 pi epsilon 0 only into 1 into 1 into 1 square, that is 1 upon 4 pi epsilon 0, that is 4 pi multiplication 8.854 into 10 to the power minus 12. Let us calculate it. we have 7 upon 22. This is 1 upon pi. Then this is also divided by 4. Then this is also divided by 8.854. This is coming 0.000, sorry, 8984. 0.008984 into 10 to the power 12. This 12 will go up. So this is coming as 3 decimal is when shifted. It will be 8.98 into 10 to the power. This 3 is subtracted from this. It will be 9. Apparently equal to 9 into 10 to the power 9. And of course this is Newton. So the final conclusion is that we have considered charge as 1. So in this term, it can be told that that amount of charge or a certain amount of charge when placed in vacuum at a distance of 1 meter and experiences a force of 10 into 10 to the power 9 newtons, then that particular charge, that particular value of charge is called 1 unit of charge. That was considered as unit, or that is considered as unit charge. So let us consider two bodies are kept in vacuum, separated 1 meter apart, and the amount of charge is being increased, and force is continuously observed by some mean. As soon as the value of force is found as 9 into 10 to the power 9 newtons, it is declared that whatever the value of charge is there given on the body is of unit value. Unit value I am using is considered as the reference, the unit for measuring other values of charge. This was explained, this was expressed by the coulomb. So the unit of charge also is considered as coulomb. So for electrostatic analysis, the unit value of charge can be defined as when certain amount of charge is kept in vacuum 1 meter apart and the force of 9 into 10 to the power 9 Newton is experienced between them, then the amount of charge given on the bodies is declared as unit charge. On the name of scientist Coulomb, this unit is named as Coulomb, denoted by C. Now, earlier for the permittivity, I have not written the unit. So, let us consider here. In terms of Coulomb as defined, the unit of permittivity can be expressed